Alrighty, so we are picking up with example 6 on section 4 of chapter 3, and it's a table. So in the directions, they give us a bunch of values for, looks like the original function, the derivative of that function, and the second derivative. So they also tell us that f of x is a twice differentiable function. So that means that it is continuous, and specifically it's continuous on this interval right here. We don't know what's going on the rest of the x values, but we know from -3 to 5, you have a continuous function, okay? And it's also differentiable. So what does that mean? Well, that means that there's no cusps. It's continuous, so there's no vertical asymptotes. There's no points of discontinuity, okay? So like whatever it is, it's a smooth curve and it's all connected. So that's what they're like telling you when they give you that information. All right, so part A. Is it safe to say that f of x is concave up on the open interval from -3 to 5? So remember, concavity is controlled by the second derivative, okay? Concave up specifically is when the second derivative is positive. So you would look over here at the second derivative, and at -3, the second derivative is 1. At 2, the second derivative is 4. And at 5, the second derivative is 0. Now, they did say the open interval from -3 to 5. So technically, we're not looking at exactly at -3 or at exactly at 5. So would it be safe to say that the function is concave up from -3 to 5? Yes or no? So, okay, so let's vote. Use the participant window and give me a check mark if you think yes. Do the X if you think no. And be ready to back up your answer. Either way.
Uh-oh, I think I need to change my answer to no.
That's what I'm saying.
You gotta be able to tell me why. While you're all thinking about it, I'm gonna put a Band-Aid on my finger. I have this horrible cut in my finger. I won't show you again. Well, I just showed you, didn't I? Cut my finger while I was slicing the ham on Thanksgiving morning. It was like nightmare. Okay, I know nobody wants to see that, so make sure I have Band-Aid on. All right, did we all vote? Oh my goodness, it's a sea of red X's. Well, why?
Because Katie said no.
Yeah, that's not a good enough answer. I don't think the reading.
I think it's my fault.
Well, actually, I think it's positive because on the open interval, which isn't including the 0 because that would be on a closed interval, they're all positive.
They're all positive. What?
The f prime of x's.
All the x's.
No, the second derivative of the x's.
Uh-huh.
Yeah.
There's a local maximum because the derivative is 0 at 2, so it must be like a hill opening down.
Hill? Could be like a dip, or it could be the top of the hill. Yeah.
But the slope is positive on one side and then changes to negative, so it must be a maximum and opening downward.
Yeah. So
I said no because like since we can't see like every single point or like just the graph, couldn't it just be wiggling around the whole time? Like we don't know what it's doing.
Yeah. We do know that the first derivative is positive and that it's negative. So we know there's some kind of dip going on there, but who knows? Maybe it dips like 5 times. All we know is that here At -3, it's this, at 2, it's this, and at 5, it's this. But we know it's all connected, but we don't know how it connects. So it could go like this, or it could go like this. I mean, who knows? And that's the thing. When you have a table, it's only one little snapshot of what they want to give you as far as information. So those of you that said the red X, the reason it's the red X, it's no, is because we are not given the entire function. We don't know what's happening on all those little decimals and fractional X values in between -3 and 2, or what's happening between 2 and 5. We don't know. So it is not safe to say, because we have limited information, or however you want to say it. You don't know what's going on in between the points. You could say that too, okay? All right. While you're writing that down, think about the answers to part B and part C. These are both old material. So explain why there must be a Z, which is just another X value. That's all that means. There must be a Z in between -3 and 5, such that the function value at that Z has got to equal 6. No trick on this one. This one's definitely like, there's a reason that you can guarantee that. So we're not looking at the derivative or anything. We're just looking at the function. So at -3, we're here. That's the Y value. At 2, we're here. And at 5, we're here. So explain why there must be a Z, which is just another X value, such that when you evaluate the function at that Z, it equals 6.
Wasn't it called like EVT?
You're close. It does end in V and T. First,
IVT? I don't know what the letter is.
that's right.
MV. IVT.
There's a lot of VTs, a lot of VTs. So this one's IVT, okay? And this was back from section 1.5. So that was a long time ago, you guys. Back when we were proving continuity. IVT is the intermediate value theorem. And that says if F is continuous on a closed interval or an open interval. I can't remember if it was closed or open, but we'll be safe and we'll just say open. That way it covers it for both. If F is continuous on a closed interval from A to B, there exists, remember the backwards E is there exists, a C in between, so a C such that C is in between A and B. What was the rest of it? And f of c equals, oh, here we go. We'll go like this. We'll do this. Make this short. So C such that C is in between A and B, then F of C has to be between F of B and F of A. I really crammed that in there, but that's basically intermediate value theorem. What does that say? If you have a continuous function, that means everything is connected. Everything is connected. So if you, let's say A is here and B is here. If you start like down here and you end up, I don't know, we'll say up here. So this point right here would be A comma F of A, and up here would be B comma F of B. And if this is a continuous function, somewhere it's going to hit every single Y value between F of A and F of B. Now, it can do whatever it wants. It can loop up and down like 50 times if it wants to. But the point is, if you're going to start down here and you're going to end up here, somehow you're going to hit every single Y value in between. It's like the example we had with temperature. If it starts out at 30 degrees in the morning and by the afternoon it reaches 50 degrees, at some point between those two times, the temperature was at every single Y value in between 30 degrees and 50 degrees. That's the intermediate value theorem. Why? Because temperature is a continuous function. We can't jump from like 2 degrees to 80 degrees without going through all the other phases, all the other degrees. So that's why. So look at what happens here. If you're at -3, the Y value is 0. And if you end at 5, the Y value at 5 is 7. So even though we're on an open interval, if we go from 0 to 7, if we go, let's see, -3, 1, 2, 3, 0. So this is -3, 0, and 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. All right, up here. So 5, 7. Whatever happens in between here, at some point, there is going to be a Y value at 6. One does exist. So that's a review of intermediate value theorem. Okay? For letter C, explain why there must be a W, which is just like another X value, in between -3 and 5, such that the first derivative at that W must be 7/8. So this is also a review. And it also ends with a V and a T. So you got 2 left to pick from. Which one is this?
Is this one MVT?
Good,
Or
right.
did I pick the wrong?
No, that's it. Got it. It's the right one. MVT, right. So what's MVT say? We just studied this. This is actually in chapter 3, so I hope you know this one well. This means that if F is continuous, which it is, and differentiable, which it is, then there exists some W such that the derivative at W equals the average rate of change, or the slope of F of 5 minus F of -3, in this case, because this is like my A and my B, all over 5 minus -3. Okay? So I don't know what this is, but I can figure this out because I can use the table for this. So F of 5 is 7 minus f of -3 is 0 all over 8. So that means that at some point, the slope of the tangent line at W is going to equal the average slope over the course from -3 to 5. So the slope of the tangent line will equal the slope of the secant line if I were to connect the points at -3 and 5. That's all you have to do with that one. Okay. Okay. D, does f of x have a local max, a local min, or neither at x equals 2? So we kind of talked about this like way back in part A. So let's like go back to it and like continue that discussion, okay? So is it a local max, is it a local min, or neither at x equals 2? Okay, and of course, whatever you're gonna say, you gotta back it up with a reason. So at 2, here we are. So the function value at 2 is 2. The first derivative at 2 is 0. And the second derivative at 2 is 4. What do you think? Somebody be brave.
I think it's impossible to determine
Why?
because on this entire function, they only give us 3 points, and there could be so many more that are higher or lower.
Yeah, true. Anything else anybody wants to add to that?
I agree.
Me too.
Ditto. Okay. Any arguments for it being a max or a min? Anything? No, nobody wants to like put up a debate about this. All right, yeah, I'll give in. So this is neither. It does lean towards, I will say, it does lean towards being a minimum because, well, actually, no, I guess not. Because these kind of like, they go against each other. Look what this says here. Like this 5 right here says the first derivative is positive. So that would mean that like the graph is going up. As you approach, like coming in from the right, you're going up. And then this 0 means that you would be flattening out. And then at 5, well, by the time we get to 5, which is a ways away from 2, I mean, it's not close by any means. So you're negative again, like that, right? So it looks like it's going up and then flat and then coming back down. But then if you look at the second derivative, well, you're getting a positive answer for the second derivative. And remember from yesterday, that controls concavity. And if you get a positive answer for the second derivative, that means you're concave up. So like these are like contradicting each other, okay? You could have something. No, actually, never mind. You can't. Or did somebody want to add something? Did anybody want to say something? I thought I saw like a microphone come on. No, maybe not. So I was thinking maybe we could do something like this, but it would still be a neither. And we can't have this part because over here we saw that it was negative. So you're right. It's neither. Not enough information. Okay. Yeah, Justin, question?
Does anybody want a single person chair? They're very cushy and comfy. We're getting rid of some chairs in our house. They're pretty big armrests too. We can just drive it over to your house because otherwise we're throwing them away.
Y'all can talk about that via email, okay? Although maybe somebody on YouTube will want a single chair after I like publish this. You never know. You might like have people getting in touch with you from who knows where. All right, send Justin like a text message if you're interested in furniture. All right, let's move on. We're gonna look at example, what do we have next? Example 7, okay? All right, so for example 7, you are given a graph of the derivative of f of a continuous function from 0 to 9. Answer the following questions in complete sentences. So what you're looking at is a velocity graph, okay? So you're looking at a derivative. Think of it maybe as velocity, okay? So part A, on what open intervals is f decreasing? So remember, this is the derivative, known, or you think of it as velocity, or think of it as slope. This is a graph of all the slopes. So on what open intervals is f decreasing? So f is going to be decreasing when the first derivative is less than 0. Okay? So tell me, when is the first derivative less than 0?
From x equals 2 to x equals 3, and then from x equals 5 to x equals 7.
That would be true if you had a graph of f, but you have a graph of the derivative of f. Be careful.
Oh,
Is it going to be whenever the graph is negative?
Yeah, so remember, this graph represents all the slopes of f. The derivative is the slope. So if you have y values that are down here below the x-axis, that means the slope of f will be negative, or f will be decreasing, okay? So we have to like change your perspective for this one, because you don't have f. You're not actually looking at the actual function. I don't know what f is. All I know is this picture is of its derivative. So when is it below the x-axis? That's when this is negative. So you would say from 0 to 1 in union with from 6 to 8. Your y values are negative, and so that's when f will be decreasing, okay? Okay. Part B, at what values of x does f have a local maximum or minimum? So let's think about this. When you have a local max or a local min, that is when your derivative equals 0 or your derivative does not exist. Like if you have like a cusp, okay? And also, the derivative has to change signs. Okay, so that's the criteria for this. In order to have like a local max or a local min, your derivative at that max or min has to be 0, because it'd be like the top of a hill or the bottom of like a hill, bottom of like a, I don't know, like a U shape, or a cusp, like a corner. And in order for it to be a max or a min, your slopes have to change. Like it has to be going up and then going down, or it has to be like coming down and then going up. So the derivative has to change signs. Where would there be a local max or a local min?
At 1, 6, and 8.
1, 6, and 8. Yeah, good. So at 1, the derivative equals 0. At 6, the derivative equals 0. And at 8, the derivative equals 0. Also, at 1, the derivative changes from negative to positive. You have y values below the x-axis and you have y values above the x-axis. Okay, so what does this mean? These negative y values means that the slope was negative on the original function. And then at 1, it flattened out to be 0. And then these y values mean that the slope turned positive again. So it came down, flattened out at 1, and then these positive y values means it went back up again. All right. At 6, oh, I put second derivative, didn't I? Sorry, first derivative. At 6, the first derivative changes from, okay, so here we are at 6. It goes from positive y values to negative y values. Positive to negative. So what's happening at 6? Well, it was going up, and then it flattened out, and then it started going down again. So another max. And then at 8, the first derivative changes from negative to positive. So you had a negative slope approaching 8. At 8, it was flat. And then after 8, it's like positive again. So it goes back up. Okay. So if it goes from negative to positive, this is a minimum. If it goes from, I'm going to draw my picture. If it goes from positive to negative, this is a max. And then this one was another negative to positive, so this is a minimum. Okay. All right, you're doing good because this is very abstract for sure. Okay, so now for letter C. Do y'all need a minute to write this down, or are you good? Good to move on. Good, okay. Awesome. All righty. Okay, so for letter C, okay, if I ever get going too fast, just take screenshots, right? Take a screenshot of whatever I got going on up here, and then you can always write it down later too. Okay, letter C, on what intervals is F concave up? All right, now you go back to what you know, right? We go back to the definition of concave up. So concavity is controlled by the second derivative. So concave up is going to be when the second derivative is greater than 0. So what we have here is a graph of the first derivative. So if you need to figure out the second derivative from this graph, the second derivative would be the slope of the first derivative. So now we're looking at slope, okay? When you start thinking about what the slopes would be along this curve, you're actually thinking about the second derivative. So what would be the intervals that your second derivative would be positive for this?
Between 0 and 2.
0 and 2, that's good.
And
Positive
3.
slope. 3 and 5.
And 7 and 9.
Yep. Good. So you have a positive slope here, positive slope here, and a positive slope here. So you are concave up. All right. So you want to think of the slopes. All right. By saying that the second derivative is greater than 0 is justification, all right, for the concave up answer. All right, now part D, state the inflection values of f. So we were talking about this in the last couple of days. The inflection values would be when the second derivative equals 0 or where the second derivative does not exist. And in order for it to be an inflection value, not only do you have to satisfy that, but the second derivative has to change signs. So, and f double prime of x changes from either negative to positive or positive to negative. Okay. So since we're still talking about the second derivative, you're still looking at that graph and analyzing its slopes, okay? So tell me where we would have inflection values.
Is that at 2, 3, 5, and 7?
2, 3, 5, 7. Good, very good. So at x equals 2, x equals 3, x equals 5, and x equals 7. Good, the slopes would be 0 at those spots. And then for the one at 2, the second derivative changes from positive to negative because the slope goes from positive to negative. And then at 3, the second derivative goes from negative to positive, negative to positive. At 5, we go from positive to negative. And at 7, negative to positive. Very good. Good. Okay, I'm writing all this down, but you can't see it. There you go. Okay, so for letter E, this is asking you to sketch a graph. So in AP Calculus, we don't really do curve sketching anymore. So I know you're all very disappointed. So what I'm gonna do is, it's actually a real pain. So I am gonna make a separate video of all the curve sketching examples and you can watch them like tomorrow or something. So for this letter E, we're gonna skip this one for now. To be honest, whenever you do a curve, like whenever you sketch a graph, there's so many different ways that you can sketch the graph and be correct that I think that's why they kind of, I don't know, College Board kind of threw it out because it's very difficult to grade because there can be so many different possibilities and it be the correct graph. So I'll do a video for you probably this afternoon or maybe tomorrow morning actually, and then you can see examples of curve sketching, but you don't have to do any curve sketching for our class this semester. So I'm gonna skip that one for now. So that'll be a video later. Okay, on to the back. Let's try this. Example number 8. All right, so you're given a derivative graph again. All right, so this is not f of x, it's actually f prime of x. We do know that this is continuous. even though its derivative is not continuous, the function, the original function is continuous. So something's going on here at like 6. There's something going on at x equals 6 with the original function to make it so that it's continuous but not differentiable at 6. There's something up there. So let's start with letter A. On what open intervals is f increasing? So when is the original function increasing? Remember, that is when the first derivative is greater than 0. When is that going to be?
Between 0 and 2.
Yep.
And 4 and 6. And 8 and 9.
Yep. So this is when the graph is above the x-axis. That's how we get this. Because all of these y values on this graph represent slopes. So like at 0, the slope is 3. At 1, the slope is, I don't know, maybe 2. At 2, the slope is 0. At 3, the slope is -1. So when you have a positive y value, that's when your slope is going to be positive. So your function will be increasing. Okay. Part B. At what values of x does f have a local maximum or minimum? So this is like kind of practicing this like we did on the other example. If you need to sneak a peek at the last example to help you figure this out, please do. So you get a local max or a min when the first derivative equals 0, or where the first derivative does not exist. And remember, we wrote this on the last example. The first derivative changes from either positive to negative or negative to positive. So how about let's start where the first derivative equals 0. Tell me the spots on this where the first derivative equals 0.
Two, 4, and 8.
Good. X equals 2, 4, and 8. Perfect. How about where the first derivative does not exist?
At 6.
Right, good. Okay, so there's all our possibilities. Now we think about the slopes, okay? Now we think about like whether the graph is changing signs from like negative to positive or positive to negative, all right? So look at 2. On either side of 2, you got positive y values and you have negative y values. So actually, let's do this. Let's make the number line like we were doing when we actually were given an equation to work with. And let's put these all on the number line. So 2, 4, 6, 8, okay? So now, instead of looking at the slope, you're looking at the actual y values because our graph is a derivative graph, okay? So to the left of 2 would be over here. Your slopes are positive. You have positive y values. In between 2 and 4, your y values are negative. Between 4 and 6, your y values are positive. Okay, remember, we're literally just looking at if we're above the x-axis or below right now. Between 6 and 8, oh, this 8 right here. Between 6 and 8, your y values are negative. And on the other side of 8, your y values are positive. Okay? Any questions about how I just filled that in? Please ask. All right, so remember, we're looking at y values because this is a derivative graph. So if you draw like a little sketch for yourself, that means slope goes up, slope goes down, up, down, up, okay? That kind of helps me anyway. So since it went up and then down at x equals 2, let's see, x equals 2, up and then down, you have a maximum. At 4, it goes down and then up, so you have a minimum. At 6, it goes up and it goes down. So at 6, you have a maximum. Okay? Now you might be thinking, how can we do that? There's no point at 6. There's no derivative at 6. But there is a point on the original function, oops, up here, because this is continuous. So what does that tell me? That tells me it must be like a cusp. Like you must have like some really pointy corner happening at 6 where the function is continuous, like it's all hooked together, but the derivative can't be done at that point. Okay. All right, and then at 8, the function goes down and then up, so you have a minimum. All right. Okay, so now we're going to go to letter C, and now it's asking us about concavity. So that's the second derivative. Concave down. So second derivative has to be negative. We're concave down when the second derivative has to be negative. In order to get the second derivative for this particular problem, you have to look at the slope of this graph. Where will the slopes of this graph be negative? What intervals?
0 to 3.
Good, 0 to 3. Any others? That's it, right? So yeah, 0 to 3. So 0 to 3, you are concave down. Good. Inflection values. So inflection values are when the second derivative is equal to 0 or where the second derivative does not exist and the second derivative changes from positive to negative or negative to positive. I know it's a lot of writing, but if you force yourself to write this down every time, you'll be good to go. Like you'll be very well prepared for either a future class, like another calculus class, or like a test, whatever, AP exam, that kind of stuff. So the inflection values are when the second derivative equals 0 or doesn't exist. So for this, you'd have to think about where the slope of this graph either equals 0 or doesn't exist. Where will that be?
3 and 6.
Good, very good. X equals 3 and X equals 6. So we could do our little number line again and put 3 and 6 on here. And this is looking at slopes of the graph. That's what you're thinking about here. Okay, so on the left of 3, your slope is negative. To the right of 3, your slope is positive. And that works all the way up to 6, is still positive. And then on the other side of 6, still positive. The slope is still positive. So where do we have our points of inflection? Are they at both points?
Is it just 3?
Yeah, good. Because at 3, this is the only spot that looks like a face. Oh man, once you see it, you can't unsee it. All right, anyway. All right, so I've been doing this for too many years. I'm starting to see like faces in the number lines. So y'all see the face or not? It's kind of pathetic, isn't it? All right, so it's winking at you. So this is going to be a point of inflection at 3 because we changed sign from negative to positive. All right, so just at x equals 3. All right. Okay, so the last one here is a curve sketching one, so I will make a video for you for that one, so we're not going to worry about that. Not right now. Okay. Okay, so that was example 8, and I think that rounds up section 3.4. Holy moly, that was a long one, wasn't it? For section 3.5, so this is really nice in 3.5 that you have this table. So if you all, like if you want to take a screenshot of that right now, or if you have it already, like, or you printed it, that's really nice. It's like all in one spot, like everything that you need to know about the original function, the first derivative, and the second derivative. So, and then down here, we already filled this in, but that's nice too to have that all in one spot. Okay. All right, so in example number 1, that's a curve sketching example. So this example right here is a curve sketching example. So I will make a video of that for you. We're not gonna worry about that right now. And so I think what I'll do, what time is it? Yeah, all right, let's do this. So there's nothing new here, guys. This is exactly the same stuff that we just talked about. So I think what I'll do is this will be the Zoom work for today. This example, and I will try to like make it show up. I guess you could just always just go into Canvas and download the notes from section 3.5, which were posted, I think, yesterday on the yesterday's module. And or take a screenshot of this right now if it shows up halfway decent on your screen. And then let's get into groups and go through these because it's probably better for you guys to talk it out with each other than to just listen to me jabber on and on. So let's do that. And I will create the breakout rooms while y'all are either downloading that or taking a screenshot. How many people do we have here today? 8. Perfect. What do we want to do? Groups of 3, groups of 2?